In this video, we'll discuss how a switching converter works and looks at each of its components in detail. A switching converter is a power supply that changes one voltage into another. Usually, it takes AC voltage from your wall and turns it into the DC voltage your devices need. This might be a finished product like a phone charger, or it might be a hidden part inside a larger device. Let's look closer at how it works. First, the AC voltage enters through a connector. This voltage must be turned into DC. We do this using 4 diodes called a bridge rectifier. This can be 4 separate diodes or one single part with 4 diodes inside. After that, we use an electrolytic capacitor to smooth out the voltage. Sometimes 2 capacitors are used in a series. In that case, we put resistors in parallel with them to act as a balancer, ensuring the voltage is divided equally between the two. There is a challenge when you first plug the device in. Because the capacitors are empty, they try to pull a huge amount of electricity instantly. This is called inrush current, and it can burn components or trip your circuit breaker. To stop this, we use an NTC resistor. When it is cold, its resistance is high, which blocks the surge. As current passes through, it heats up and its resistance drops so power can flow normally. In powerful units, a relay is used to bypass the NTC once the system is running to save energy. We use a fuse at the input of an SMPS to protect it from damage. If there is a short circuit, overload, or fault, too much current flows. The fuse melts and cuts the power, stopping damage to the SMPS and preventing fire or shock. Now we have constant DC voltage and we need to convert it to the specific voltage we want. For safety, most converters that use city electricity need isolation, which means the input side and output side are not physically connected. We achieve this using a transformer. One of the most popular isolated designs is the flyback converter. It uses a transformer, a switch, usually a MOSFET, a diode, and a capacitor. When the switch is turned on, the transformer stores energy from the input in its magnetic field. When the switch turns off, it releases that stored energy to the output. This happens thousands of times every second. Because it works at such a high frequency, these converters can be much smaller than linear power supplies. However, transformers are not perfect. When the switch turns off, some energy gets trapped in the primary side. This is called leakage energy. If it isn't handled, it creates a voltage spike that can destroy the MOSFET. We solve this by adding a separate path for that energy to go, called a RCD Snubber circuit. The flyback design is great for low power up to about 200 watts. For higher power, we use other design like forward to switch forward, half bridge, full bridge, or resonant converters. If you would like to learn more about resonant converters, you can watch the suggested videos. The brain of the system is a controller IC. Its job is to turn the switch on and off at exactly the right time. It sends high-frequency pulse to the MOSFET, usually through a small gate resistor to control the switching speed. In a high-power system, a driver circuit might be used. Sometimes the IC need to monitor the current. In small units, we use a shunt resistor, but in high-power units, a shunt creates too much heat, so we use a current transformer instead. The IC also needs a stable reference voltage, and it uses a clock to keep time, which is generated by charging and discharging a small external capacitor. To keep the output voltage steady, even if the load changes, we take feedback from the output using a resistive divider. This might include a potentiometer so you can adjust the voltage precisely. This signal goes through a compensation circuit, usually using a TL431 regulator, and then through an optocoupler. If you would like to learn more about TL431, you can watch the suggested video. The optocoupler is very important because it uses light to send the signal back to the controller IC, keeping the high voltage side safely isolated from the output side. You may ask, how does the controller chip turn on if the power is needed only appear after the power supply starts switching? To solve this, we use a startup circuit. It slowly charges a capacitor until the voltage is high enough for the IC to wake up. Once the IC starts switching the MOSFET, an auxiliary winding on the transformer takes over and provides the running power. We often use a Zener diode here to protect the IC and capacitor from getting too much voltage if something goes wrong. If the voltage drops too low, the IC turns off and tries to start up process again. Finally, we have to deal with heat and noise. Switching a MOSFET so fast creates heat, so we attach it to a heatsink. It also creates electrical noise because components are not ideal. Diodes, transformers, and even the isolation on the MOSFET have parasitic properties, like hidden tiny capacitors. Because switching circuits have fast voltage change with high dV/dt, high-frequency circulating currents are generated and flow through parasitic capacitors and cause interference in the power supply or in other electrical equipment. To fix this, we use an EMI filter at the input. This filter uses an inductor called a common mode choke and a special capacitor. It creates a wall that can effectively block the noise. For safety, we add resistors to drain the charge from the filter capacitor. Using a snubber circuit also helps reduce this noise by smoothing out the high dV/dt noise. Enjoying the content? Give a like, subscribe for more power electronics tutorial. Don't miss out. Now let's look at an industrial example, a 100 watt power supply. The AC voltage enters the board through a wire and connects to the input terminal. The first component is a fuse for protection, followed by an NTC to handle the initial power surge. The electricity passes through the EMI filter and reaches the bridge rectifier. We have resistors placed here to safely discharge the filter capacitors. You can also see an electrolytic capacitor which smooths the voltage into a steady DC. To keep the board safe from vibration, some silicone adhesive is used to hold the large parts in place. In this section, we find the switching circuit. It includes the transformer, MOSFET, diode, and capacitor, which together form the flyback converter. There is also an air core coil that acts as an inductor. It works with the capacitor to create a filter that reduces the ripple in the output voltage. You can see a shunt resistor for current feedback. There is also a snubber circuit nearby to protect the MOSFET. If we look at the bottom of the board, we find the PWM controller IC. This IC receives a signal from the output through an optocoupler to control the power. The IC gets its own running power from an auxiliary winding on the transformer. Finally, there is a potentiometer so the user can fine-tune the output voltage and an LED to show that the power is on. Now let's examine a much larger 600 watt power supply. As you can see, this is much more complex because the power is higher. It needs more parts. The input power enters here and passes through a two-stage EMI filter using two common mode inductors. There is an NTC here as well, but in this high power module, it is bypassed by a relay once the system starts up to save energy. These capacitors are connected through a manual 110 220 volt switch. When the switch is set to 110 volts, it changes the connection between the bridge rectifier and the capacitor, creating a different current path. This allows the capacitor to charge in a way that results in a higher DC voltage level across them. This power supply uses two MOSFETs and has output inductors right after the secondary diodes, which tells us this is a half-bridge converter. The main transformer is in the center. Next to it, there is a polyester capacitor, which blocks DC voltage to prevent the transformer from saturation. There is also a small pulse transformer used to drive the MOSFETs and a current transformer to monitor the power levels. In this design, the main controller is on the secondary side, which is why you don't see an optocoupler for feedback. Because 600 watts creates a lot of heat, there is a large heatsink and a cooling fan. There is even a thermal switch that will shut everything down if it gets too hot. Finally, there is a tiny separate flyback power supply just to provide the standby power for the controller and the fan. If this video was useful to you, please support the channel by leaving a like and a comment. Stay tuned for our next video. Thank you.